Hi everyone, thanks for tuning in here to our first video in Unit 2. The title of Unit 2 is called The Derivative. And today we're going to be starting with our first lesson where we're going to actually talk about what the heck is a derivative, and more specifically, what's the formula and how do we derive it? How do we derive the formula to find a derivative? Okay? Well, here, look what I have here on your packet. Deriving the formula for derivative, the slope of a curve at a point. What? The slope of a curve? Up until now, yeah, you've heard the word slope, but it was always related to linear functions, lines. Like, we know for sure lines have slope. But now in calculus, we're going to talk about curves having slope, because they do. You can find the rate of change on a curve just like you can find the rate of change on a line. So on the back of this packet, I just drew some pictures here for you. It's just some key ingredients we're going to need to get through this lesson. I thought back to geometry, and when you studied circles in geometry, I want to go over some vocabulary. You learned in geometry that if you draw a line through a circle and it touches the circle in two places, that is a specific kind of line, and it's called a secant line. You might also remember, like, if you take off the line part of this and just make it a line segment, that's a chord. But the line is called a secant line. Now, you also learned that if you draw a line and it just touches one point on your circle, this is actually called a tangent line. And this vocabulary is going to be coming up in just a few minutes, so I wanted to remind you of that. And you can have a tangent line anywhere around the circle. You could have one here. You could have one down here. The thing you got to know about a tangent line, though, is that if you draw a tangent line, it follows like the contour of the shape that you're drawing the tangent line at. So you wouldn't want to draw a tangent line at this point, like coming this way, because look at the curve. You want to kind of follow the structure of the curve when you draw a tangent line. Okay, so down here I wrote, can a curve have slope? Yes, it can. I just drew a quadratic function here. Here's a parabola, and I isolated a point here. Even though this is not linear, you can zone in on this point, okay, and look at the structure of your graph. Look at that. And you can approximate that curve right there using a tangent line. Look at this, tangent line approximates the curve. Imagine if you could just kind of flatten this part out from here to here. If you could just flatten that into this line, you just found the rate of change of this curve at this point. So yes, curves can have slope, and that's what the derivative is. So that's what we're going to study today, or start to study today. So we're going to flip our packet back over and go through our notes, which is basically the first and second page of this packet. So number 1 says, let P, which is right here, let P be a fixed point on a curve, and then let Q be a nearby movable point on that curve. Okay, boom, I've got it. Number 2, it says, now consider the line through P and Q called a blank line. Well, the first thing I'm going to do is take a ruler, and I'm going to draw the line connecting P and Q right there. And what is that line called? Well, do you see how it's hitting the curve twice? That's going to be a secant line. I'm actually going to switch colors here. Secant line. So you can go ahead and fill that in. Secant line. Okay. Now number 3 says, suppose that the curve is the graph of f of x. Okay, graph of f of x. We can determine the coordinates of P and Q. So we're going to go ahead and give P some coordinates, and we're also going to go up here and give Q its own little set of coordinates. And these coordinates, I've got to warn you, are going to be very generic, because I want my learning today, my formula for slope of a curve, to be able to work on any graph I like. So I'm going to make this really generic. So let's take a look at P. P has an x value of x. That's how generic we're going to make that. We're going to say that P is situated at the x value of x on the x-axis. Well, that makes our y value at P f of x. The function's value when x is x. So the coordinates then generically at P are going to be x, comma, f of x. It's like saying xy, right? X f of x. All right, now we go to Q. Now we got to get a little creative with Q, so I'm going to drag this down here. My x value at Q, I am going to call it x plus h. X plus a little bit more. Now that forces this distance to be h, so I'll mark it as such. So we have x and we have x plus a little bit more. Well, what does that make the y value at Q? Well, you have to take your function, f, and evaluate it at this x coordinate. So x plus h. So this is f of x plus h. So the coordinates then at Q are x plus h for the x and f of x plus h for the y value. Okay, so we've got coordinates at P. Let me box those in. We've got coordinates here at P, and we've got coordinates here at Q. All right, moving on. Number 3. Oh, I already read number 3, but let's bring this down. So now that we used our picture to find this, let's just write here for ourselves a little note. So the coordinates at P are x f of x, and then the coordinates at Q are x plus h, comma, f of x plus h. There we go. Now things start to get interesting. Number 4 says the slope, let me highlight this, the slope of the secant line through P and Q is, and look, this is Algebra 1, you guys. This isn't calculus, this is Algebra 1. Remember this formula from Alg 1? It says that the slope of a line, in this case the slope of my secant line up here, this guy right here, is just the change in y over the change in x, or better known as y sub 2 minus y sub 1 over x sub 2 minus x sub 1. I mean, we've got a line. We got 2 coordinates here. So like this one here, we'll call this x sub 1, y sub 1. And we'll call this x sub 2, y sub 2. x1, y1, x sub 2, y sub 2, okay? So using this formula then, I can write that the slope of this secant line, okay, let's set this up. Here's my fraction bar, my minuses. I need y sub 2. Well, y sub 2 is right here. It's f of x plus h, okay? Minus y sub 1, it's right here, f of x. All over x sub 2, that's x plus h, minus x sub 1, that's just x. So I hope you guys, this red pen, this was x plus h, this was f of x plus h, and this was x and f of x. So just making sure you're good here, seeing those coordinates coming down here. And then the last thing that'll happen here, see how these x's here will cross out, cross out, cross out. So my final answer here for my slope of my secant line is f of x plus h, which was the y value at Q, minus the y value at P, all over h. That's the only thing left on the bottom there. Okay, so this is just Algebra 1. We drew a line. Algebra 1, simple. Now flip it. I'm going to fill in some blanks over here. It says, now suppose we start sliding point Q closer and closer to point P. What is happening to H? Okay, so let me actually grab another sheet here so I don't have to keep flip-flopping. Hold tight. Grab another sheet here. So if Q is sliding closer and closer to P. So remember, we had this secant line right here. Now say we pick up Q and we move it like right here. Let's say that's Q sub 1, like the first stopping place for Q. And we draw a new secant line. It would look like this. Or say we move Q even closer to P and called that Q sub 2 and drew another secant line. See how things are changing? The slope is certainly getting less steep as Q slides toward P, but they're actually asking me here, what is happening to H? Well, H was the distance on the x-axis here. This was H. So as Q slides toward P, I hope you're thinking, well, H is shrinking. In fact, H is approaching 0. Notice the word approaching. Makes me think of limits, interestingly enough. So H is approaching 0. Well, what is happening to the secant line? Well, take a look. The secant line, yeah, it's getting less steep, but can you imagine if Q just kept sliding and sliding and sliding and sliding toward P? Doesn't it kind of look like the tangent line, or the secant line? Look at it here, 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 here. It keeps getting closer and closer. Eventually, as H shrinks towards 0, the secant line will approach the tangent line at P. As Q gets infinitely close to P, the secant line is approaching tangency. So that's what we're going to write in this next blank. What is happening to the secant line? We're going to say the secant line is approaching, sorry, my hands are like all over this, is approaching the tangent line at P. That's what's happening to the secant line. And so letter C, it's kind of redundant. I'm saying here, as Q approaches P, the secant line is, typo, that should say approaching the tangent line. The tangent line, okay? So, the definition of tangent line, are you ready? The tangent line at P, okay, the tangent line at P is the limiting, oh my gosh, there's the word limit, the limiting, approaching, oh goodness, I feel limits coming on. The tangent line at P is the limiting position of the secant line as Q moves toward P along the curve. So as H slides to 0, the secant line approaches the tangent line. The tangent line is the limit, the limiting position of the secant line as Q comes toward P. So we're getting there. We're almost there. The rate of change of a curve. Here's our quick recap. From the front side, we wrote down that the slope of the secant line between P and Q was equal to f of x plus h, that was the second y, minus the first y, all over the second x minus the first x. That's just copied from the front. Here we go, slope of the tangent line. You click and drag. You take the same formula, f of x plus h minus f of x. See, this is a slope. This is a slope from Algebra 1. But to change it from the secant line to the tangent line is the limiting position of the secant line as h slides towards 0. So now you have tangency. You are at P and you have tangency. So you have now found the rate of change of your curve. This is the slope of the tangent line at a point. And we have now come to the definition of derivative. Derivative is the slope of a tangent line at a fixed point given by, and here's the formula. This is the one to memorize. Okay, We write it in a fancy way. We start with m, slope. We subscript it with TAN for slope of the tangent line. And then we draw this vertical bar. And we say to ourselves, okay, I'm finding the slope of the tangent line at any point, fixed point, x, f of x. Now, this point represents, let's go back to our curve, the front page here, P. Remember P? P was at x, f of x, right? So that's where we are. So the slope of the tangent line at the point x, f of x is given by, and then we just recopy this formula, the limit as h slides towards 0. The slope is going to be changing as we slide towards 0 of f of x plus h minus f of x all over h. This, I can't highlight this enough, this is the formula to find derivative. And in the next video, we're going to use it to get specific with specific functions and find the slopes of specific curves. So tune into the next video. On that video, we're going to tackle example 1, part A.